So welcome everyone to the third lecture of the mini course, Introduction to Quantum Groups and Hopf Algebras. I'm Gastón Andrés García from the University of La Plata in Argentina, and we are going to do examples now of quantum groups. So we are going to study some examples in this third lecture about quantum coordinate algebras, and in the last lecture about quantum enveloping algebras. These are the two families of quantum groups. And people study different quantum groups for different purposes. So if someone tells you a quantum group, then you should ask which one. Yes. So in this lecture, we are going to see the first example. I based all the two lectures before on this example. Actually, I work a lot in the other example, but okay, I work a lot also in this kind of example. So we are going to leave behind the classical settings, reconstruction theorem, and things like that, and we're going to look at the quantum setting. Yes? And how do we going to define quantum groups or quantum things? The quantum things, so we want to take our classical object, the coordinate algebra of a group, and we want to define something like a deformation. How do we do that? So one idea is, this idea works in the general case. We proved last lecture that this thing is the coend of a functor. So what was that? It was simply the thing generated by matrix coefficients. Of representations of G. So the problem is, okay, we want to construct something like this, but do we need all representations? The answer is no. For some examples, for example, if we take SL2 like G, say over the complex numbers, we need only one, the standard representation. So we need only one family of representations, so we need only one family of matrix coefficients. So how do we construct it? This, we make a stop here. The representation of SL2, I will explain that in the last lecture. This is the group of matrices of determinant 1, and the representations are very well known. The standard representations is just the action on column vectors. Matrices by column vectors, and that's it. So a matrix times a column vector, I don't know how to call it, no, not A, I don't know, XY, it's just the multiplication, okay? A, B, C, D is the multiplication, AX plus BY, CX plus DY. This is the standard representation, and with these matrix coefficients, this one, you generate everything. So how do we quantize something? So this is the standard representation. Say, let's call it V. And how do we get something quantum? One way is to deform the representation and then take matrix coefficients. And this is actually a path that one could take to define this object. So one defines representations, one deforms the representations. In the case of SL2, it's enough to deform this one, but for other groups, you need to deform more ones. And you take the matrix coefficients, and the thing here is of some representations. Because if not, we get in trouble, okay? The some representations are the ones that are good in the classical case, okay? We need some properties of the classical case without quantum things. And to keep these properties, we have to restrict to our representations. And then we take matrix coefficients, and then voila. So this can be done more or less for any group, and this is the process. For example, there are some examples in the literature of when G is, as I said, SL over the complex numbers, or is the symplectic group, the orthogonal groups, superorthogonal, orthogonal, let's say orthogonal, and so on, okay? So very explicit examples following this strategy. Well, we are not going to make this strategy because I don't want to talk about representations because it will take me a lot. So I'm going to present you exactly the deformation of this algebra that gives me this one. So by a presentation, just a formula. And then we will try, the idea is, okay, why do you form something like this and not in another way? Then we will find a method how to deform something with formulas, explicit formulas, not coming from representations. But actually, what is going on in reality is that the representations appear in measures. When someone is measured something, appears in this level, representations. So the representations are deformed. So to get the quantum group of the algebraic object, one takes the matrix coefficients. That is the idea. And when one takes the matrix coefficients, this is the quantum group that we are getting. Okay, so we're going to talk about Sn. So today we fix our attention on SLN, the simplest one. And for this one, for this case, there's a lot of literature that make it that is great because they make a lot of computations and the theorems are very nice described. This is, for example, for SL2 in the case in the book of Kassel, Christian Kassel. And for SLN and GLN, there is a memoir of the AMS written by Parcel 1. They have a lot of computations there. And for general groups, there's a book of Ken Brown and Ken Good there. It's also a very nice reference. Of course, there's a lot of, in quantum groups we have a lot of references, but I will follow these three ones for the things I'm going to talk about. If I get some time, I will talk about recent result of mine with a colleague in Buenos Aires. Okay, so that's the perspective for today. So this is magic. Coming out of the blue, we have this deformation of the matrix algebra. Not the matrix algebra itself, is the functions on the matrices. As I'm trying to recall from the first lecture, I defined the functions of matrices as being just the polynomial ring of n square variables. Yeah, and this is the polynomial ring. So we have n square variables and everything is commutative. So what we are doing here is saying, okay, they are not going to be commutative anymore, but not in any strange sense. So we are saying for some letters they commute, almost commute, but the difference is a q. What is a q? Okay, a q for us will be any number, but not 0. Why not 0? Because when we take 0, the example collapses, so we get nothing. So we get very strange things, so we don't take q equal to 0. In the last lecture, we're going to see why we don't take q equal to 0, because it makes no sense. So up to now, we say, okay, q is not 0, and we get this algebra with this relation. So we still have monomials that commute, that these ones, but the other ones you see here is very strange. So let me write for n equal to 2 what are these relations, because here it depends on if the subindices are less or equal than the other one, so it's kind of strange. So let me write for n equal 2. For n equal 2, so to not write in subindices, let me write x11 equal to a, x12 equal to b, x21 equal to c, and x22 equal to d. Okay? So I write less on the blackboard. So in this case, the OQ of M2 is generated by these 4 letters satisfying the following relations. AC, let's start with the first row. AB is Q, BA. So A and B, Q commute. We say Q commute. A and C is Q, CA. So Q commute. CD is, let's start first with B. BC is CB. They commute. BD is QDB. CB and CA, we have it here. So is CD equal to QDC. And the last one is AD minus DA is Q minus 1 BC. So these are the relations for n equal to 2. As I said, Q could be any number. If we put Q equal to 1, then we get our algebra. So it means that it's a kind of quantization. When Q is equal to 1, we get the classical case. So we are quantizing our functions algebra on the matrices. And actually, this is the thing is, we deformed the multiplication. But we knew that our algebra, this algebra, was a bialgebra because we defined a coproduct and a counit. But if we change the multiplication, maybe we lose the structure of the coalgebra. But this is not the case. We still have a coalgebra structure. It is a proposition. One has to prove that this is okay. Okay? And how do we prove that it is okay? Because the thing is, we define a linear map. So actually, we are defining an algebra map on the generators. So delta is well defined. if, for example, it holds that the relation holds. So I go back for the relation, so we need to check the relations. For example, so one way to say that is that the relation holds, or that the ideal of relation is a B-ideal. It's the same thing. But let's do one relation. What do I mean by that? So if we apply the co-multiplication on one side, should be the same as applying the co-multiplication on the other side. Yeah, so we need to prove that. And how do we prove that? By hand, okay? So we compute this side, and then we compute this side, and then we check that we have the same, but taking into account all the relations, yes? So let's do that. So we'll change color. Now, let's keep it with white. So with the first one, so now I will going to use all the power of my definition. So I said that this one should be an algebra map. So this thing should be equal to this thing, the product of the two coproducts. And then we take the formula for this one, which is the dual of the multiplication of matrices. Now we'll put this, no, okay. I will put the K there, or I don't know if it's a good letter or not. Okay, let's keep with that. X, K, R. And the other one, I don't have any space. Say L, this is K, 1 to N, L, 1 to N, of X, J, L, tensor, X, L, R. So now we multiply everything. And how do we multiply? By applying the distributivity. And how do we multiply the tensors? First tensor with first tensor, second tensor with second tensor. So we get a double sum of this one. Xik, Xjl tensor, XKR, XLR. That's it. That's one side. Okay? So now we go and compute the second one and try to figure out why they are the same. So let's compute the second one. So first thing, it should be linear, so the number goes out. Second thing, it is an algebra map, so it is the co-multiplication here times the co-multiplication here. So I will skip that step and write exactly these sums, but in the inverse order, because here they are in inverse order. Not this, yes, these sums. So this is JL tensor LR, and here is K equal to 1 to N, X IK tensor X KR. We do again the same procedure and we multiply them. So we have KL from 1 to N. Now I will put the Q outside and put the parentheses, okay? So we have XJL XIK tensor XLR XKR. And these two things should be the same. Okay? Now we have to use all the properties of this thing to prove that they are actually equal. Okay? So the first thing is, okay, let's look at the slide. One of the properties there is comparing when the subindices has the monomial has one subindices that is equal to the other one. We have an R on in the second subindex or in the first subindex. So we will look at that in this here, okay? And of course, we want to compare this one with this one. So we are going to first assume okay, let's recall first that I am trying to prove something for I less than j, okay? So I'm assuming that I is less than j. So to change the things here, for example, if we look at this monomial, in the slide says that we know how to change this with the q or a minus q if this is less than this. Okay? So I will first write the sum separating the cases when L is less than k, when L is equal to k, and when L is bigger than k. So we will understand more or less what is going on. So this is equal, so we put the q outside. So first we assume that L is less than k, okay? And we write this. Plus the sum when they are equal plus the sum when L is bigger than k. Okay? I have a strange feeling because I use different letters as in my notes, so I don't know what is going on because I want to use something and something strange happens. So let me check this out. IR, JR, it's okay, it's okay, it's okay. And the other one, JR, IR, it's okay, it's okay, it's okay. JL, IK, LR, KR. Okay, should be good, okay? Yeah, okay. All right, then. Now, we know that I is less than j, and L is bigger than k. So we have a mixed thing. So when one is bigger and the no, we have these two are bigger than these two. So when these two are bigger than these two, this is the last one. Okay, is the last equation. When the first two subindices are less than the second two, index by index, then we have to use the second formula. What does the second formula say? What it's saying? We change the order, but if we change the order of these two, then we have to add the term on the left. So this thing is, we change the order, we put the IK first and the JL second, but then we have to put the term, this one. And some x. Which x? We have to interchange them. We have to interchange the subindex. So in the first one is we replace the first one with the I, so we keep IL, and the second with the second, JK. So now we perform this change, and then we have to prove that actually what is going on. Okay, let's compute the resulting thing. So the resulting thing is, I will work with only this one, and then I will cancel some things that if they appear. So if we change this term by this thing, is the following we get. Instead of this, we put this one here, XIK, XJL. And we have to add the following two with this one. So we have plus sum for L bigger than K of Q times this one, XIL, XJK, tensor. I will write the second one with Q minus 1, because if not, I will forget, okay? This is with the minus, and this is with the plus. Yeah, I think I didn't make any mistake. So now we look at this thing with patience, and the thing is, L is bigger than K. Yes, if L is bigger than K, so something should cancel, and what is the one that it should cancel? Let's look at. Which one is canceling? So you see here, with the first one and the last one, we have the roles interchanged, okay? Okay, I'm very confused on that. It should be simple. So if here L is less than K, this one is q times x kr x lr. And there should be a minus somewhere, and with this minus, so I change this one. I'll take this one, q minus 1, with these two, so if I apply the second equation to this one, but on the other side, because L is bigger than K, I change the other with the q minus 1, and I erase the q minus 1. So we have here LR, KR. No, I changed the order. KR, LR with a minus. So the thing is, we actually can cancel this one with this one. I think I'm getting this straight. I don't know what is going on. Sorry about that. I think I have to perform the computation again. It's a mess always. I prepare this, but this is a mess. Or help me. Are you seeing something that I'm not seeing because I make the change and it doesn't seem to work? So everything is correct. J, L, L, R, I, K, K, R, it's okay. So these ones should be, these are all equal. And if this is bigger, then it means that they are in the other way around. If they are in the other way around, I'll change the order here. I'm not changing the order here, so I'll change the order here, and we put KR, LR, we put the Q minus 1 here in the front. Okay. Let me go back. So control set, let's control set the things. So I will go back to where I was lost. So I will write exactly what I have here. Okay, I will go back to this point. So in this point, the thing is, in these sums, the L is less than K. And in these sums, the L is bigger than K, okay? And when we have the second subindex equal, we look at the relation, and we can compare these two. This one is Q minus time this one, or in other words, this one is Q times this one. So we change this one with the Q minus 1. Yes? KR, LR. And then I perform the change again. So this is, so trust me now. So I'm doing everything okay or not? Because there was a minus there. there was a minus somewhere. Okay. Because the j is bigger than than I, so I was doing I was changing the terms in the wrong way with the minus. Everything because of a minus. So I have this one to change this one. This is the second term in the summand. In the last equation, the second summand is this one with different letters because j is bigger than I and L and here is k. Here is k. J is bigger than I and L is bigger than k. So this is the second term with the minus. So I want to change this one. So to change this one, the plus is, I changed with the plus, IKJL. And then the other term comes with the minus. This is the minus that I wanted. So with the minus, it was a q minus 1, and I take a q of the sum of the first change, IL x jk, plus q minus 2 with this one. Now we see that this term is equal to this term. It's not equal to this term, this one. This one is equal to this one. We have xik, xik, xjl, xjl. No, this is not the true. Sorry, I'm a mathematician, so I have to say the truth. So this is not true. What I have to look at is this one. And if I'm doing something wrong, because, no, it is okay. Yes, it is wrong, because I changed this badly. I'm using the relation badly, so this is, sorry again, this is JKIL. So, we have XJL, XIK, XJK, XIL. So the K and the L's are inverted, and here the K's and the L are inverted. But here, we are assuming that L is less than K, and here that L is bigger than K. So if we interchange the roles with L and K, this is 1, so we have a minus, here we have a plus, so we can cancel these two terms. This one with this one. And we have remaining the other terms. The other terms, we change them accordingly to what we want to do. Okay, we have a q outside, and this q should be gone somehow. And why this should be gone somehow? So let me recall this side is xik, xjl, tensor, x kr, xlr. So we should obtain this thing. So this thing is this one. So we have this one. When we put the q with this one, it is gone. Okay. So this sum is this sum. It's okay. So this one is not the one like this one, because the j is in the first term and the I is there. So we have to interchange these two. These two are the same, so it doesn't matter. If we interchange these two, because j is bigger than I, let's write the colors. So I wanted to make an example, and you see live what is going on. And when you see live what is going on, this happens in quantum group theory. You have to be careful about the signs and everything. You put a q minus 1 if you interchange these two. But with the q outside, then we get that the term is exactly this one, which is exactly this one, and the other one, the last one, you interchange the things 2 times, because here we have KR, LR, we are okay, but here IL is in front of JRL. This should be a K. Or what? I don't remember what I wrote. No, this was JK IL. One interchange these things, and then you get that these things is exact. This is the sum with L bigger than K. Here you interchange the rows. Here L is equal to K, and then you arrange the things, and you get the sum of LK equal exactly this one. But with the do I change the letters? No, let's take this one. So what was the idea that I wanted to show you? That this is by brute force that one can prove one relation using one proof that delta is well defined using the relations. And I did it only for one equation, and you have to do it for all of them. So you have to be careful to using the equations and seeing what is going on with the subindices, but it works, okay? So trust me that it works. This is because I changed the subindices in my notation, so I have to think everything again, and in the blackboard it's kind of messy, but it works. So if you still are missed what is going on, you can do it in 2 by 2, yeah? In 2 by 2, I will write 2 by 2 equations here, so we'll keep this. The equations in 2 by 2 were AB was equal to QBA, AC is QCA, BC is equal to CB, BD is equal to QDB, and what else? CD is equal to QDC. And the last one, AD, that I used in the computation, but with the problem was my minus BC. Okay. So these are the relations for 2 by 2. So the thing is, you have to keep track of the commutation by this number. So I wanted to do it in a general case, but there's a mess with the subindices. And 2 by 2 is clear, so I'm going to do the next computation with 2 by 2. So what we prove is this thing is a non-commutative and non-concommutative bialgebra. It is not a Hopf algebra, so it does not correspond to a group. Why? Because there is an element that is group-like. So what happens when we have a group-like element? So suppose we have an element that satisfies this thing. Yes? If the multiplication of this element is true, and we have a Hopf algebra, then the property of the Hopf algebra is that this thing should be equal to this thing. But and of course, the other thing is that this thing, the counit, should satisfy this property. These are the axioms of the Hopf algebras applied to this particular element if it satisfies this. From this equation, we see that in any group-like element, the co-multiplication should be 1. So the element is not 0, okay? If this is 1, this is 1. So S of G is the inverse, should be the inverse. Okay? But all the elements in our algebra are polynomials. So we have to have inverses of polynomials. But in this algebra, we don't have inverses of polynomials because of the degree. So we have no thing that when we multiply to a polynomial, then we get 1. So there is no way that this thing is a Hopf algebra. It is a bi-algebra, okay? And every time you have an element like this, it should have an inverse. So, okay, what should we do to have something that is quantum? Okay, there exists something that helped us to find inverses. In the classical case was the determinant. If the determinant of any matrix is not 0, then the matrix is invertible. Now we change the commutation properties of our algebra, and we have no determinant anymore, but we have something that is called a quantum determinant. So the quantum determinant, for example, for this algebra is AD minus QBC. So you see, when I put Q equal to 1, I get the formula of the determinant. And magic, it works, okay? The quantum determinant is a central element, and it is a group-like element, as one would expect. Okay, why is central? Let's prove that it's central. So I will do again a commutation relation, so help me. And we see that it's central, so it commutes with everything. So let's do it with A, say, I don't know, A. We take A and multiply by the determinant, okay? And we want to show that the A goes to the other side. So this is A of AD minus QBC. So we have A squared minus Q, A, BC. And we start to put in the A on the other side. So if we put A on the other side, we have I am using the last one. So the last relation is this one. If we change AD, we have to change it AD by DA, this thing. Where is the plus? Thank you. Thank you, because this is important. And minus Q. If we change AB, we have the Q squared, BAC. So I will do it again. We have A. Let's do the multiplication here. No. I won't change this one because it's going to blow away. So minus Q ABC. So I have ADA plus Q ABC minus Q minus 1 ABC minus Q ABC. So this one goes away with this one. And I change again the AD with the DA. No, I don't change anything. So we have AD A minus Q minus 1 A B C. So let's put the A here at the back. So if I change AB with BA, then a Q appears. So Q with Q minus 1 goes away. So we have ADA minus BAC. Now we change the A with the C, and then we have ADA minus QBCA. So the A is on the right, so we have AD minus Q BC A, which is exactly the determinant times A. So I make always the sign mistake. It is terrible when one works with super quantum groups. So I wanted to show you live how do you do the calculations. So then in this way one shows that the quantum determinant is central. You can do it in general way, but it's a mess with sub-indices, but it's the same idea. You have to work hard and then you prove it that is central, and in the same way you prove that it's a group-like. So it satisfies this thing. Yeah? You prove the equality and then you get it. So we have a group-like element that is central. So it works like the determinant, and so we quantize our definition for this the quantum group SLN. What was the algebra of function over SLN? Was the algebra of functions of any matrices divided the ideal generated by the determinant minus 1. So here we have the quantum determinant, so we replace the quantum determinant, the determinant by the quantum determinant, and the functions on the matrices by the quantum functions, and then we have a definition of the quantum, another quantum by algebra, that is the quantum functions algebra over the SLN. We can do the same for the general group, which are the invertible matrices, and for this thing we need that the determinant is invertible. So we invent an element which is called T, that is the inverse of the determinant. The T is like we are inverting one polynomial. We are not inverting all polynomials, only one, that is the determinant. And with this work. So again, the good thing is when adding only the determinant, we get Hopf algebras. This is crazy. With only the determinant, the quantum determinant, we get Hopf algebras. How do you prove that? Okay, you prove that the ideals that I include here, that these two ideals are Hopf ideals. It means they are two-sided ideals, and they are well-behaved with respect to the coproduct, and they are B ideals. And then one can define the antipode using the determinant as one does for the classical case. How do we define the antipode? A matrix is invertible if the determinant is not 0. And for that we have a formula. The formula for an inverse of a matrix is given by the adjoint matrix divided the determinant. And this is exactly what we do. For example, when n is equal to 2, the antipode of this matrix is the adjoint matrix multiplied by the inverse of the determinant. Now, the adjoint matrix is not our matrix, the adjoint classical matrix, because we are using the quantum determinant. So some q's appears here, that if q is equal to 1, we get what we know, the adjoint matrix of this one. But since we are using the quantum determinant, some q's appear. So everything, the q's appears everywhere because we are changing the multiplication. And the thing is, if we put q equal to 1, we get what we know in the classical case. Yes? So as I said, I post these 3 slides very slowly, because if you want to do that, you have a week, more or less, on computations. No, a week not, but one afternoon, one morning, you compute a lot of these things, but it can be done. It's only computations, okay? So you have to have the idea what to do, and then it's hard work. As I show you here, it's hard work. And without making mistakes with the signs, as I did. But at least you see what can happen if you do the computations. Not everything is perfect. So, now I think it's a good time to stop. So let's stop for 5, 6 minutes. And then we are going to relate our quantum group with the algebra, the functions algebra of what we know, or of any group. They are deeply related. So now it's time for questions. So ask any question that you want.
So
Yes.
The inverse of the quantum determinant, you assume that is there?
Yes, you put an extra element. It's a very good question. So, for example, in this example, you have these letters, and there are polynomials in these letters. And you have this determinant that is also polynomial. So actually, to do that, to invert that, you invent an element t. And how do you include the element t in the algebra? You add it. You put the element, you take your algebra, and you put one element more. So polynomials with this t. So you add one more variable. And you declare that is the inverse of this one by saying you take the quotient of this thing. So you're saying is the inverse of that one. Do you see there? No. You say you take the idea, this idea. So you take the relation that this should be 1. So you declare it is the inverse. So this process is called the localization on the element that you want to invert. In mathematics, you can abstractly invert anything by this idea. You declare and you put an inverse. The thing that could happen is that when you put something that is wrong, everything collapses, and the examples that you have is 0 equal to 1 or something like that. But if you can prove that it does not collapse, it is a new thing. And the relation for SL, you put this one equal to 1. Yeah? You declare that it's 1, and then you're done. Okay? Okay, let's go for the questions. There's subindices with the questions. Well, the first question. What are the properties of the quantum determinant? The quantum determinant is a function, okay, a polynomial. Is the thing that you say it is multiplicative, you are seeing the determinant as an element and not as a function. When you say it is multiplicative, the other way around, you are saying that as a function and not as an element. Here I'm saying it as an element because it is a polynomial. As a function is multiplicative if as an element is a group-like element. This is what I was saying in the first class. The property that is multiplicative is this property, that it is a group-like element, okay? And this is, when you prove this, you are saying it is, as a function, if you put any matrix there, is multiplicative. Why? Because if you remember that the co-multiplication is the transpose of the multiplication, so the thing is, if we put matrices, say, in here, this is not quite right, okay? Because you cannot put matrices because you cannot go back to groups, to geometry. But suppose you can. If you can, or just put the determinant, which is also a group-like element. So the determinant in the product of two matrices is the determinant of each one. So the property of being multiplicative, the determinant is multiplicative, is the property of being group-like, of this function being group-like. You can realize the determinant as, it's not as a module, but if I have time, maybe not. I was planning to talk about this. The determinant is an element in our algebra. It's not a representation, but it is very connected with a representation, and we find this as a co-representation, not as a representation. The co-representation of an exterior algebra. Okay. And yes, you can find the quantum determinant like this. And actually, we have general formulas for different quantum determinants. Say, I will say only this. And it's exactly that. It's a very good question. The determinant is detected in the exterior power. You're right. But if you quantize the thing like this, you don't have exterior powers anymore. You have Q exterior powers or different versions of exterior powers. And with that exterior powers, then you have determinants. And yes, we have quantum trace, and it is defined in a categorical way, the quantum trace. Oh, the ring-theoretic properties when Q change, there are a lot of results concerning that. I'm going to talk about this now with the specializations, but we have a lot of papers about when Q change and the ring-theoretical properties. A lot of people study that, if they are semi-prime or things like that. There are a lot, so I cannot resume them in a kind of couple of minutes. Okay? Sorry. If they are Morita equivalent, no. For example, if we have Q equal to 1, it's not Morita equivalent to Q equal the root of unity. I think if Q is, not sure. Between 0 and 1, I think it's not true. I'm not sure, because I don't know, but maybe not. No, they are not Morita equivalent. So we have different objects. They are actually different objects. Yes, we have a lot. The commutativity, for example, when Q is a root of unity, these algebras are, when I'm saying, are co-semi-simple, without the Q. With Q equal to 1 are co-semi-simple. And with Q, root of unity, they are not co-semi-simple anymore. So they are very different, okay? And the thing is, the cases are separated in Q equal to 1, Q equal to a root of unity, and the other ones. In the algebraic setting, we work with Q equal a root of unity, and in the analysis setting, in the operator algebra setting, they work with Q equal a number between 0 and 1, because they keep the cosine simplicity. Okay, I will stop with the question 1, and then I will answer the 2 when I'm done. So we keep the class going on. And the property, in geometrically speaking, the properties work for Q generic. They have almost more or less the same properties when the Q is not a root of unity. So we say that Q is generic in this case, and they have more or less the same properties, okay? So, okay, I'm back. Let me check if someone else asked something, because I was answering the question of Fauci. No, okay. There's only one question more. I thought it was more items for 2. Okay, I will answer this question later. Okay, so about the question if what if we change the Q as we want? And this is what I'm going to answer now. But for some Qs, the thing is, when we use Q between Q that is not the root of unity, everything more or less is the same. The algebra have more or less the same properties. I think the same properties. Yes, the same properties. And you treat them as a unique case, when Q is not the root of unity. Then we have Q equal to 1, that is our commutative case, and when Q is a root of unity. And when Q is a root of unity, strange things happen. When Q is not the root of unity, the properties are very similar to the ones when Q is equal to 1. In some reason, maybe that, or the idea could be that we can deform the Q nicely in a way that it approaches to 1 as we want. But if we take the Q's into the circle, yes, into the circumference of radius 1, then we cannot approach, we cannot move freely everywhere. So these things are strange. So the behavior when Q when the Q is the root of unity are related to things what happens in positive characteristic. So it's very strange phenomenon. So let me show you what is going on. Now I have to put it. So let's go and specialize. We do the specialization at 1, at root of 1. So we take an odd element, an odd natural number, and take a primitive root of unity. Okay? So if you want, you may take Q equal to E 2 pi I L divided N. Okay? Let's take this one. And L is odd. If not, we get into trouble because we are going to talk about the SLN. So the first thing is, because of the relation, if we take the L power of the xij, then we get a central element. And this is because of the relations. So we go back to the relations. If we put the x, we see the relations, they are Q commutative. So if some element is elevated to the L power, when we commute, then it turns out to have Q to the L. But Q to the L is 1. So they commute with everyone. So when we take the elements to the L, they are central. And the second point is another very, very, very critical point. Again, by the co-multiplication. I'm saying that the co-multiplication of the elements to the L is the same as not putting the L, but putting the L, okay? It's strange. Why is this strange? Because of the following. I will tell you the idea. I wanted to do the whole computation, but I made a mistake in the first one. It took me a while to do it properly, and I didn't take it perfectly. So I will give you the idea of what is going on, and you finish the computations by yourself. So again, we want to compute this thing. So delta is, the co-multiplication is an algebra map. So to compute this thing, you have to compute this thing. do the co-multiplication of one object and then to the L. But this thing is the sum to the L. So we have to compute the L power of a sum. So we can write this thing like we split the sum in two when k is less than n. Plus the last term. When k, yeah, this is n, the last term is n, nj, yes, to the L. So we have, if we put names to this one, let's put the name y to this one and x to all this one. So we have, the thing is x plus y to the L. We have to compute this. No? To see that is actually what is going on. But this thing is, in the commutative case, is I don't know which letter to use. Let's put, I don't know. I already used K and L. M. So if we use our knowledge of the binomial formula of Newton's binomial formula, we know that this is true, okay? I'm not sure if I write this in this order or the other one. Yes. It is important if in the non-commutative case. Let me check. Short checking. Okay. Yes. So this is in the commutative case, but we are not in the commutative case. We are in the Q-commutative case. So if we assume that this is true, the Q-commute, then everything has to be changed. And how do we change this? We put here a Q. So what? The binomial formula still holds. This is the famous Q binomial formula. Yes? And this is the hypothesis that the two terms Q commute. Here, the two terms Q square commute, but it's the same. We are replacing Q with the Q squared. And we have to change the binomial by the Q binomial. And what is the Q binomial? Okay, first we define what is a Q number. A Q number is, if Q is not 1, is defined like this. Qm minus 1 divided by Q minus 1. If Q is 1, this is the same as writing Qm minus 1, Qm minus 2, is Q plus 1. So you see, when you put Q equal to 1, the Q number, M1, is just M, because we have M minus 2. We have M terms here. So we define the Q factorial numbers, which are the Q numbers as one may imagine. Yes, this is the Q number, the Q factorial, and define the combinatorial M, LM by LQ factorial divided by L minus M Q factorial. Here is L minus M. M. Some remarks about this. Suppose that we take Q a root of unity. If we take the Q and L root of unity, this is, if we look at here, QL is 1. So if we put L instead of M, we get 0. So a Q number gives us 0 if we put exactly the order of the root. And every time this term appears, then this is 0. This number is 0. So actually, what holds is that the combinatorial Q, this is the Q, is 0 when the M is not 0 and not L. It's in between. So it's a kind of, let me move this. It's kind of weird, but it's very nice. These numbers work very nicely, very, very nicely. And when you take the root of unity, and then some things are 0. This is why everything changes when we take root of unity and when you don't take root of unity. So in this case, so let me go back to this formula. If Q is a root of unity, is an L root of unity, all the terms are 0 if M is not 0 or L. So they all go away. So if they all go away, we get the first one and the last one. So we get L0 Q where M is 0, so we get X to the L. And LL Q Y to the L. But this is, by definition, 1, and this is, by definition, 1. So it's like in school, when you do the kids, the kids now, the young girls and boys, in the first year of the university, a lot of people do this mistake. This is true for Q numbers. So if the variable Q commute, this is true. Amazing. So using this is why the co-multiplication turns out to be that you can split the sum into the powers, and here is where the L's appear. Yeah, and then you apply inductions on this one, and then you go down, 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 and you get all the summands to the L. So here we are using the Q commutations and the Q numbers. So this is very important to have a root of unity, because if we don't have a root of unity, this is not true. Okay? So this is a very special case for root of unity. And this helps us to connect the classical case with the quantum case, because we can define a map. Frobenius defined this map on matrices. Frobenius, this is a very, not on matrices, on finite fields and things like that. Frobenius maps are maps that you take the numbers and you put them to a power of a prime number, of something. Yes? So this is a quantum version of the Frobenius map. And instead of raising the elements of the matrix to some power, we are raising the matrix coefficients to some power. And for example, to the L. And this is very nice because we know that these coordinate functions to the L are central. So in the left-hand side, here, everything is commutative. And when we go here, the image is commutative, and the elements here are central. So this map respects the commutativity of this thing. So we have everything here, everything that we have here, we have it here, and it is injective. And actually, more nice things happen. Okay, as I proved this property, I didn't prove it, but I gave the idea. It behaves well with the co-multiplications and the co-unit. So actually, it's a bi-algebra morphism, and it's injective. It's a monomorphism. And the determinant of here, our determinant, goes to the Q determinant to the L. Yeah? And this is not so easy to prove. You can prove it by hand in the 2x2 example, but in general, you need a better idea, okay? You have to think better. And this is done in the book or in the memoir of Partial and Wang. It's a long computation. All what I'm saying takes a lot of time, so pages and pages of computations. So, but as this course is short, it's not a semester long, I'm trying to give you the idea so you can go back to books or things like that, and you can do the exercises and try to do the computations, okay? But the thing is, I want to give you the idea, and then when you have idea, then the other thing is practice. Okay, since the Frobenius map behaves very well with the determinant, we can take the quotients on both sides. If we take the quotients on the right-hand side, on the left-hand side, sorry, in the other way around, on the left-hand side, we get the algebraic functions over the special linear group or the general linear group, okay? So we have a relations with the quantum, the groups and the quantum groups. So the functions on a group and the functions on the quantum group. They are inside. They are inside. So the quantum group, when Q is a root of unity, has inside the classical theory. So the quantum thing has inside the classical thing. So the thing is, how different is the quantum thing to the classical thing? Because they have the inside. How big is that inside here? It is too different or not? Well, I would say, okay, should be more or less equal because we are taking the L power. Well, okay, yes, it is quite near it. And we have a short exact sequence of Hopf algebras, or whatever it is. It is saying that the difference between our quantum thing and the classical thing is a finite dimensional thing. So anything quantum is something classical with something else that is finite dimensional. And we can control this A. More or less, the idea is that we have to understand what is this A to understand the thing in the middle. For example, this situation is very nice when one studies representation theories and things like that. We can reduce all the problems in here from knowing the problems here and here. Actually, as vector spaces, the quantum group is the tensor product of the classical thing and this A. I'm going to talk about this A in the last lecture. And this is not only as vector spaces, it has the structure of modules and comodules. Okay? And this is difficult to prove in general, that we have this situation, that we have a cleft exact sequence of Hopf algebras. Doesn't matter, this is very technical, but when we prove that, we are saying, yeah, don't worry, the quantum group, as strange as it might be, is the classical group, the classical function algebra, and something else that is finite dimensional. So the quantum properties of this thing is encoded in this finite dimensional thing. And finite dimensional is very good for working. It's not infinite dimensional. Okay, are there any questions for so far up to now? Besides the question that I left, the two. So the idea is I introduce a deformation by hand here. For example, in the 2x2 case, I took this deformation of the multiplication. So why can you can ask, why do you take this one and not other one? Yeah, because it has no reason, it's arbitrary. Well, we have a lot of options how to deform the multiplication. And a way to do that was introduced by these three guys, Fadev, Reshetikhin, and Takhtayan. They were part of the St. Petersburg school, and they introduced what is now called the FRT construction. FRT because Fadev, Reshetikhin, and Takhtayan. The idea is construct all these quantum groups by general method. What is the general method? It's based on the symmetry in the representation category. So you remember that I said we are looking at some objects that have the property that the representations or co-representations satisfies that we can sum the representations, that the field is a representation, and the dual is representation. Now we want more. We want to interchange the representations on the sides. And this is asking to the category to be more rigid, more things. And this is encoded in what is called a braiding or a symmetry, okay? We want to interchange the tensor product of two representations because this is happening in the experiment. So we want to interchange them. But, okay, suppose we know the formula for interchange two things. The idea is, knowing that formula for interchanging two things, we construct a quantum group. That was a fantastic idea. So the idea is, we take only one comodule. Yeah, remember that we are not working with modules, but comodules, because we are working with functions algebras that are naturally the co-algebras for something, so we are working with comodules. And so you take one comodule, and the comodule we can change the comodule with itself using this symmetry, yeah? And the idea is this symmetry should be a comodule map. With these two ingredients, we construct a function algebra, okay? So that's the idea. We construct a function algebra. So first we construct what should be our comodule. Take a finite dimensional vector space with a basis, V1, Vn. And take any endomorphism of the tensor product. Yes? So what is an endomorphism of the tensor product? Is what I wrote before. So we go from V tensor V to V tensor V. Yeah? It's a linear map. So any linear map can be described using basis. So a basis of V tensor V is the basis of V tensor the basis of V in all the possible orders. So we make the basis is given by this one, Vi tensor Vj. This is the basis of V tensor V. And the linear map in an element of the basis is a linear combination of the elements of the basis. This is our numbers. Of course, I have 4 indices because 2 corresponds to where the element that I'm coming from, and 2 corresponds to the element of the linear combination, okay? So we have 4. This is terrible, it is terrible, but it is what it is. So we have 4 elements. So, okay, that's a map. So now we want to construct a function algebra. So let's start very simple. Take a vector space, not an algebra. Take a vector space spanned by some letters, xij. So xij would be the matrix coefficient of something, okay? So you take xij. So with the vector space xij, we already have a coalgebra. And the coalgebra has the formula, the well-known formula that I was talking about 3 days ago. 3 days in a row. this one that reminds us the multiplications of matrices. So I am saying here that I'm considering the xij as matrix coefficients. Okay? And that's it. We stop there because we are okay. This is a coalgebra. We don't need multiplications or things like that. It's a linear map satisfying this one. Okay. And V is actually a left comodal with this one, with this very general formula given here. Okay? So we can always do that. So for any vector space, we can construct a comodal. So all right, great. We constructed a comodal in a very general way for this coalgebra, this genetic coalgebra. But the thing is, okay, we go back. We want a comodal map between the tensor product of V tensor V, not only V. So we need to give a comodular structure on V tensor V. So not only on V, but on the product of V tensor V. So we need to add multiplication of our variables. So how do we multiply variables? In a very monstrous way. Multiply them all in any order and don't put any restrictions. Okay? So multiply them all. What is that? The tensor algebra. Yeah, this is just the tensor algebra. Come on. Yeah. It's the polynomial ring of non-commutative variables. And it's a coalgebra by declaring delta and epsilon B algebra maps. And everything is done as I did. So how do you compute the co-multiplications? But multiplying the results, as I did before. And here it's easier and more complicated in the same way, because if you multiply two things, that it stays in the same order, because we don't have a commutation rules. So it stays like this. So it's terrible, but it is what it is. So with this one, V tensor V is a left comodal by doing this thing. And the idea is that we have the co-modular structure for Vi, that is Xik tensor Vk. And we have the comodular structure for Vj. And the idea is we multiply these two things in order. This one with this one, and this one with this one, but with this one we put the tensor. So we are doing the things so that the comodular structure is respect the multiplication in the algebra. Yes, this is the natural way of co-multiplying a product of things in the tensor product. Okay, this one is a comodal. So what do we want? We want an algebra that V is a comodal and this map is a comodal map. So you see that here we need the multiplication of the variables. They have to multiply them by themselves. So this is why we need to take the algebra generated by these elements. So we want this to be a comodal map. And following the commutation diagrams that I introduced you in the first lecture, this means the following. So here is, in the first row, is the map, C. Here is the comodal map that I defined before. Yes? So Vi tensor Vj goes to this element, which is the one that I wrote in the blackboard. So instead of going down and then applying the map identity tensor C, we go up, apply C, the transformation. The transformation has this formula. These are the elements, the coefficients that we don't know, okay? They are general coefficients. And then we apply the formula for the comodal, and we get something. okay, this something should be equal to this something. Terrible, okay? But if we look carefully, the last two tensors are the same. So if the last two tensors are the same, they are a basis, it means that the sums in the first tensor should be equal for any R and any S. So this gives us a formula for the our algebra. And if these two things are equal, then we have a conditions on our map to be a comodal map. And this is what we ask for. The FRT construction for or the universal quantum semigroup, this is called in some papers, is given by the algebra generated by xij's, our xij's that are matrix coefficients, divided this very strange relation. And why do we have these strange relations? Because we want the braiding, or this form to change the things, to be a communal map, just like this. So it's a very weird relation, and we're going to see examples. So how do we get some commuting relations? We have to find solutions of these equations by replacing the C by some numbers that we want. So if you find a solution for this thing, then not a solution. You give numbers and then you get the equations. For some numbers, you get one conditions. For other numbers, you get another condition. For example, if you put 0, the C are all zeros, then this condition disappears, and our bialgebra is just the tensor one. And then it depends on what you put on the C's. So this construction makes sense for any map between V, tensor V, but we are going to concentrate on some specific maps that are solutions of the braid equation. And this is not an equation because of that, coming out of the blue. This equation is equivalent to the quantum Yang-Baxter equation, which is what was the origin of this one. This thing has to do with the quantum Yang-Baxter equation, okay? Solution of the quantum Yang-Baxter equation. This is a method to produce solution of the quantum Yang-Baxter equation, which is actually equivalent to the braid equation, and we work with the braid equation, which is easy to write. So the theorem is one can always construct the algebra like that, and one can prove the following. It's a bialgebra, always is a bialgebra. The V, our very general vector space is an A comodal. The map C is a comodal map, and it has the following universal property. Why it is important to have a universal property? It's important because every time you have a universal property, your element is unique up to isomorphism. So if someone finds another element that satisfies the same properties, it's yours, okay? Maybe the definition is different, the deformation is another thing. This theorem is saying it's the same object, don't worry. And the property is that it's universal with respect to the coaction. So we have our B is a comodal, and if we have another algebra, I didn't change this file. If we have another algebra, there should be a B. There's a typo there. If we have another algebra, or this A prime, that V is also a comodal, then we have a map from EC to A such that this commutes. So the algebra is more or less unique up to isomorphism, or we have always a map. In other words, okay? We can relate always the algebras like this. So example. Let's take for example, the endomorphism V of dimension n, and the endomorphism with this formula. Yeah? Just take the formula like this, and with this formula, for example, in 2 by 2, we have this matrix. So the basis I'm taking in 2 by 2 is ordered like this: B1 tensor V1, B1 tensor V2, B2 tensor V1, B2 tensor V2. So with this formula here, the matrix is this one. With this matrix, tarang, our AC is our quantum function algebra over the matrices. So if you change the matrix, you get another thing. Sometimes you change the matrix and you get another thing that is isomorphic to your algebra that you start with. Okay? But it gives you a lot of possible quantizations. So to finish this class, I'm going to talk about how to construct, how do we construct a Hopf algebra from this example, because the theorem tells us that we have always a bialgebra, but we are looking for functions on a group, okay? Why? Because we want the properties of the representation theory. Not a bialgebra, but a Hopf algebra. So we want a Hopf algebra, not a bialgebra only. So how do we get a bialgebra from a quantum group or a Hopf algebra from this bialgebra? Okay, we try to reproduce the idea that I showed you before. There should be a determinant, and then we use the determinant to define the quantum group. So we need to find and prove that the existence of determinants. Schauenburg did it without that. He showed that it is always possible to define a Hopf algebra, but in a very abstract way. So this Hopf algebra is huge. We add more elements that should be the antipode of our elements. So we didn't like this definition so much. We want to find something that is explicit, more explicit than this theorem. So the idea is, can we obtain the same Hopf algebra but using the quantum determinant? So this is a tricky question, because what is a quantum determinant? The quantum determinant was defined in a very specific way by something like this. And this has to do with that matrix. What if we change the matrix? How would we find the quantum determinant? Well, we have to look for to copy the idea of the classical idea of the determinant. And if we do that, then we can do it. So what is the classical idea of the determinant? You know, the determinant is a function of matrices that tells us when a matrix is invertible or not. So, okay, forget about that. So what is the very notion of the determinant? Okay, let's think about geometry. The determinant tells us the volume of something, yes? So let's work with that. It tells us the volume. So how do we get volumes with exterior powers of things, thinking about differential geometry? So we are going to look for things that are constructed with exterior powers in the following way. Okay? So this is the idea I just told you. We want to find quantum determinants. And the idea is once you find the quantum determinants, we add the inverse of the determinant, and then we get our algebra. This is what we have done with Marco Farinati. So quantum determinants. The idea, the classical case, is the following. So we know that the matrices act on the space of columns by multiplying. So if we go to the functions, it means that the arrows are reverted. The functions coact naturally on the space of columns. And the action is the one I gave you before. Yes? This is always the same. This is the dual definition of the matrix multiplication. Yes? It is the row of the matrix times the column vector. And this is what you do. Yeah? So, okay. So for any vector space, this function algebra coacts on it. And as I showed you before, we can extend this coaction to the tensor algebra, as I did it here in the blackboard. Yes? We can extend this like this, by multiplying the first terms. So we have an action on the tensor algebra. The tensor algebra is the sum of all the power, the tensor power. The first term is the field, the second term is V, the third term is V times Z, and so on. So each tensor power is a module. Why? Because each tensor power here, if we co-multiply this, if we coact on this, then here we get the same amount of tensors. Here, if we have S here we end with S. So any tensor power is a comodule. For example, moreover, we have submodules of this tensor algebra, which is the one given by this one. Okay, this is submodule. It is a submodule, and if we make the quotient, we get a comodule. And this comodule is the exterior algebra. So, all in all, what I have proved in 2 slides is that the exterior power of this V is a comodule. Okay, what is the good thing? The tensor algebra is huge, has infinite dimension, is too big. We divide by something, and then suddenly this is finite dimensional. Great. It is finite dimensional, and each summand of this one is a comodule. But we know from differential geometry, or I don't know the course you have taken, that if we go to the power n of the exterior algebra, this is spanned by only one element. That is this element. This element is called the volume element in the exterior power. And here are only multiples of this element. If we co-multiply this element, this should be, again, this element, because it is a comodule. We have only one element there. We put here, it is an element of the algebra. Okay? This here. And because of the axiom of the co-multiplication, this element is a group-like element. And actually, when you do the computations, do it by hand at home. Yes, it is a very nice exercise. This element is actually the determinant. So the question about how do we find the determinant, it was not a question, it was in the question also. How do we find the determinant as something? The determinant appears as in the co-action of the matrices in the volume element. Yeah? So the determinant and the volume element are related. So what do we do to quantize this thing? We have to quantize the exterior algebra. So we have to understand the exterior algebra. Yeah. So the more general idea that we find is we replace the exterior algebra by something very weird. Yeah? And the very weird is we took the essential properties of the exterior algebra and put them into the definition. So first, it should be a comodule algebra. So it is an algebra and a comodule. It is graded, so it is separated in grades. The first term is the field. The second term is the vector space itself. It is finite dimensional, and in the last summand of the grading, the dimension is 1. So this is exactly the property of the exterior algebra. And one property more, that the multiplication with the first term, with the term 1, with the top minus 1, is the last one. Top, we know that it's last one top, but we are saying that it's non-degenerate. Okay, if you multiply two things that are not 0, you don't get 0. And the same in the reverse order. So, the first question that you may ask, do you have examples for such thing? Yes. if A is the algebra of functions on a matrix, such a B is the exterior algebra. Okay, but what if you take another A? You take the bialgebra given by the one that you gave me before, OQ of Mn, the quantum function algebra on the matrices. Do you have a B like that? Yes, we have. Actually, we have a lot of B's like that. And a source of examples are what we call Nichols algebra. So with these properties, we can define, again, what is a volume element and what is the quantum determinant. So first, there is a volume element because the last summand of our algebra B is just the multiples of one element because the condition was that this one was dimension 1. This is the volume element, a volume element, because any multiple of this one is also a volume element. And the quantum determinant is the element appearing in the co-multiplication. And it turns out that the quantum determinant does not depend on the multiple of the V. You can take any volume element. It gives you the same quantum determinant. And as I told you before, we have a lot of examples of the algebras B in case they are finite dimensional. And I'm cheating here because finding that a Nichols algebra is finite dimensional, I'm not going to give to you the definition of Nichols algebra because it takes too long. But we have a process, we have something to construct, we can construct something that satisfies these properties. We have a lot of examples and a lot of examples for any braid in C. You give me a braid in C, we have a lot of examples and then you have to compute them. And the difficult thing is to prove that they are finite dimensional. Once you have done that, then you can construct quantum determinants. For example, for the braiding, let's take a very easy one. Take the set, just the set having two elements. And as a braiding, takes first the functions as sets, not linear, not anything. The function is take the 1 and 2 goes to the 1, 2, the 2, 1 to the 2, 1, but the 1, 1 to the 2, 2, and the 2, 2 to the 1, 1. So it is interchanging the x times x. How do we get a solution of the braid equation like this? We just linearize these things, make linear combination of these things, and voila, we have a solution of the braid equation. So for this solution, for this linearization with a minus, we construct the algebra A with the FRT construction. The FRT construction gives us a lot of equations. The equations are all quadratics, always, and we have this thing. Yeah? This thing corresponds to this map. If we change this map, the relation changes, okay? This is why the relation changes the relation, okay? The Nichols algebra, don't worry about it. We can compute the Nichols algebra also using the computer in this case. Is the tensor algebra in these two variables with these relations. X squared plus y squared is 0, 2xy is 0, and 2yx is 0. So if the characteristic is not 2, the dimension is finite. And the basis is, actually the dimension is 4, and the basis of the B is 1, x, y, and x squared. The volume element is x squared. We have a volume element. And the determinant, the quantum determinant, is a squared minus b squared, which is central in this case. But in general, it is not central. And look that here, our algebra is not commutative because AB is not BA, it's CD. So it is a quantization, but not depending on a number. It's a quantization depending on this function. So quantum groups depend on the symmetry, how we interchange two things. The first definition came from the fact that I use a a non-specific matrix. But in general, the quantization is related to the symmetry of interchanging two representations in the tensor product. So it is hidden there, okay? And in this case, we have a central group element. We can add the inverse as we did before, and we get something called the quantum GLN, which is not like quantum, is related to this function, and the antipode is given by this thing. So we got a Hopf algebra, and actually is the Hopf algebra of Schauenburg. So this is all what I wanted to say. Thank you very much. So now I'm open for questions. There was a lot of things in the chat. So I will start reading it. First of all, yes, someone already answered that the videos are going to be shared. And before the curiosity questions, I go back to the question 2 of Fauci in the first stop in the pause. If we have an homotopy theory or homotopic underpinning quantum groups, so one can define a modular structure and category of rings. What is, actually, I don't know, I'm not sure if an homotopy theory exists. What it does exist in the quantum algebras are theories of deformation in cohomology. So the problem with homotopy and cohomology in quantum algebras is that the quantum algebras are Hopf algebras. The Hopf algebras has the structure of algebra and coalgebra. All the theories of homotopy on an algebra, or homotopy or cohomology or homology look at the algebra structure or the coalgebra structure. But here we have both. And you have to mix the both theory, and the resulting thing is that the homotopy groups and the cohomology groups or homology groups are no longer groups. So you may describe a kind of cohomology or things like that, but you have no tools because they are sets with strange things. So computing the deformation of the infinitesimal deformations or the deformation of degree 1 or 2 for something like this is difficult because we have no tools, no theoretical tools, because they have no structure. So if you have to find some deformation by computing cohomology, you have to do it by hand. And if you find something, you don't know if that find something is everything or not. So you have to compute if they are everything or not, and so it's complicated. So the theory gets stuck in that because you have to put together the algebra and the coalgebra structure, and this is a mess. If you forget the coalgebra structure, you get partial answers, but it does not reflect the quantum structure. If you look at the coalgebra structure, it's the same, okay? And if you consider both, you have to take another theory of cohomology or deformations that you cannot have the complete answer of things. I hope I answered your question, more or less. Okay, the Bertsinian supermodel in supersetting, I don't know that. I didn't study that. But I will have to look at it. The idea is that a lot of people is looking at Nichols algebra in physics because they appear like this, like generalizations of exterior algebras, or they appear in Schubert calculus and things like that. And yeah, some I think that the paper of Bereznikov talks about Nichols algebra in this sense, in physics. And there's a paper of Lettner that appeared in Advances talking about Nichols algebras in physics and conformal field theory. And the reason that they appear is because of this thing. They appear as comodal things. And we gave the definition of the weakly graded Frobenius because we had some examples of some algebras that were not Nichols algebras, they were more general, and they work. But with Nichols algebra, you're okay. So if you concentrate on finding Nichols algebra for that, it's okay. So thank you very much. Any other questions? I am sorry because of the computation today, of the sign computation. If I have time, I will include the computation in the slides, so when I upload the slides. So if you don't have any question, yes? So I'll see you in the next class in lecture 4. Bye-bye.